All right, let's get right into it. We're going to go deep inside the world of industrial machinery to uncover a hidden war. It's this relentless, silent attack that can cause total catastrophic failure, often before anyone even knows it's happening. Today, we're going full forensic investigator on the thermal assault on mechanical seals.
So what is this invisible force, this silent killer? The crazy thing is, it's something that's hiding in plain sight. We often just dismiss it as a normal part of running a machine. But you know what? Its effects can be absolutely devastating.
And the culprit? Nope, it's not just your everyday friction or things getting old, it's heat. We're talking about excessive, relentless temperature that wages a full-scale assault on the very parts that are supposed to hold our most critical systems together.
Okay, so before we can really analyze the crime, we have to get to know the victim, right? Let's start with the mechanical seal itself. It's a component that plays a role that is way, way bigger than its size would suggest.
You know, I just love this description from the source material by Dr. Ashok Punde, Silent Sentinels. Isn't that perfect? It just perfectly captures what they do. They stand guard, totally unseen, protecting the integrity of an entire system. If they fail, the whole show stops. Period.
So what's its job in a nutshell? Basically, it stops stuff from leaking out where a spinning part meets a stationary part. You know, think of a propeller shaft on a boat or a massive pump in a chemical plant. The seal is what keeps the ocean outside the boat or the chemicals inside the pump. It sounds simple, but trust me, the engineering behind it is absolutely mind-blowing.
And now, it's time to meet the villain of our story. And you have to understand, heat isn't just a passive condition here. In the world of mechanical seals, it is an active and incredibly aggressive adversary. Check this number out. This represents a fundamental rule of chemistry that you just can't ignore. For every tiny 10 degrees Celsius increase in temperature, the rate of a chemical reaction pretty much doubles. Doubles!
So what does that mean? It means temperature is a multiplier. It's literally like putting your foot on the gas pedal for every single destructive process you can imagine. Corrosion, wear, material breakdown, all of it. A small bump in temperature doesn't just make things a little worse, it can make them exponentially worse, turning a kind of manageable situation into a full-blown critical failure.
Okay, so how exactly does this thermal assault lead to a total breakdown? Let's go full CSI here, put on our investigator hats, and examine the evidence piece by piece.
Our first stop, the elastomers. These are the O-rings and other flexible, kind of rubbery parts. You can think of them as the soft tissues of the seal, designed to be flexible and create that perfect tight barrier.
But under that thermal assault, all that flexibility just, poof, it vanishes. The material gets hard and brittle, kind of like an old rubber band you find in a junk drawer that just snaps the second you try to stretch it. Once that happens, it's not sealing anything anymore. And it gets even crazier. In some cases, the heat can make the material swell up, blister, or even just vaporize completely, leaving a huge gap where a seal used to be. Now, let's move to the absolute heart of the seal, the faces. We're talking about two ultra-flat, highly polished surfaces, one that's still and one that's rotating, pressed right up against each other. The source material calls this the system's handshake, which is just a perfect way to describe this precise, intimate connection. But heat comes along and turns that polite handshake into a violent wrestling match. It can cause something called heat checking, basically a spider web of tiny cracks that ruins the surface. In some fluids, heat will literally bake deposits onto the faces. That's called coking. And that gunk acts just like sandpaper, grinding grooves into everything. All this damage just destroys the tiny thin film of liquid that's supposed to be lubricating them. And this quote just nails the result. That once perfect, low-friction connection becomes a grinding, high-friction struggle for survival. And it's a vicious cycle, right? The grinding creates more friction, which creates more heat, which creates more grinding. The seal just starts to eat itself alive.
So you're probably thinking, okay, but the metal part should be fine, right? The springs, the retainers, the skeleton of the seal, they're built for strength. Well, you'd be wrong. They are not immune to this assault at all.
Remember how we said heat is a catalyst? Well, it puts chemical corrosion into overdrive, just munching away at even hardened steel. At the same time, it makes critical parts like metal bellows get tired, they fatigue, they lose their springiness, and eventually they just crack under the pressure. The entire skeleton of the seal just slowly gives up.
But here's where it gets really, really nasty. The real danger isn't just one of these things happening on its own. It's when they start happening together.
Heat is like a ringleader that loves to bring its accomplices to the party, creating failures that are so much worse than the sum of their parts. This is where the damage really multiplies. So, for example, when you combine that baked-on gunk with poor lubrication, the seal faces don't just wear down, they can seize up completely. Just freeze. Or if you have those little micro cracks from heat checking, and then add an aggressive chemical, the surface doesn't just erode, it can literally fragment into pieces. Each problem just makes the other one 10 times worse.
Okay, I know, that was a lot of doom and gloom, but here is the good news. This assault can absolutely be prevented. And it's not about fighting heat. It's about designing for resilience and actually respecting its power.
So the key here is a proactive, multi-layered strategy. It all starts with choosing the right materials from day one, like elastomers that can actually take the heat, and super hard faces like silicon carbide that resist wear. Then you have to manage it actively. Use flush systems to constantly carry heat away from the seal, and use sensors to monitor temperatures in real time. And finally, it takes disciplined maintenance, replacing parts based on their actual thermal history, not just some generic schedule.
And this brings us to this really powerful final thought from the source material. Instead of seeing temperature as this enemy that we have to defeat, we should see it as a teacher. It's teaching us about the limits of our materials, the limits of our designs.
And honestly, that's the real takeaway here. Every squeak, every temperature spike, every little sign of wear, that's data. It's a message. So the final question isn't just about seals, it's about everything we build and operate. So ask yourself, what is your equipment trying to teach you about its limits right now?